Hi everyone. In this video, we'll continue our discussion of the calculus of inverse trig functions. It's time to talk about the derivative of arctan. This derivative is 1 over 1 plus x squared, and the proof of this is almost identical to what I showed you with arcsine in the previous video, so I'll skip those details here and encourage you to just check them for yourself, but you can trust me that this formula is true. Once we know the derivative of arctan x, we can take the derivative of arctan u, where u is something more than just an x. That would just be 1 over 1 plus u squared times the derivative of u according to the chain rule. Next up, we now know a function whose derivative is 1 over 1 plus u squared. That would be arctan of u. Notice that 1 plus u squared represents a sum of squares, so it would be nice if we had a formula for a more general sum of squares, such as a squared plus u squared, rather than just 1 plus u squared, which is quite limiting. And the formula is this: 1 over a arctan of u over a. If you like, this last formula can also be proved using pretty much the same ideas shown in the previous video with arcsine, so pause and convince yourself of that as necessary, and also pause to take a moment to record these four on your formula sheet. Let's try an example. In the previous video, I suggested you always keep an eye out for differences of squares, but the arctan formulas we came up with suggest that we should also watch for sums of squares. In this case, we can see the denominator as a sum of squares by writing it as I've just done here. And by writing it that way, this structure of a squared plus u squared is more visible. In this case, we can see a would be root 5 and u would be 2x. However, if I want to think of 2x as u, then it's necessary to perform a substitution properly, meaning we also need to account for du. A quick calculation shows that dx would be equivalent to 1/2 of du, and with that we can express our integral as 1 over root 5 squared plus u squared, and our dx can be replaced with 1/2 du. This now exactly matches the form of the last formula given on the previous slide, where a equals root 5. So we can declare this as 1 over root 5 arctan of u over root 5. As a final step, remember to put this back in terms of x, and you're done. Let's take a moment to reflect on the problem that we just did. You might have noticed that this function is of the form linear over irreducible quadratic. So it's a partial fraction. In the past, we showed that we can anti-differentiate these types of partial fractions if they're of the form f prime over f, but this one is not of that form. So studying arctan has helped us put another dent in that problem of anti-differentiating partial fractions. And actually, it turns out that every partial fraction of this type can be dealt with either by forming a sum of squares and using arctan like we did here, or by thinking of f prime over f. Sometimes it's necessary to do both of those things, but really those are the only two ingredients we need for tackling these types of partial fractions. I'll dedicate an entire video to that in the near future to help you tie all those concepts together. So for now, you can take what I've just said as a preview of what's coming soon. Let's try another example. Pause and try this one for yourself, and when you're ready to be spoiled, let's look at the solution. If you've been listening to me carefully, I suggested there are two really important things that you should always be looking out for in this course. Those things are sums and differences of squares and integrals of the form f prime over f. Of course, this isn't strictly a rule. You know, there are some problems that need only one of these two concepts. There's some problems that need both of them, and some problems that need neither of them. But keeping these two things in mind will get you through the vast majority of integral problems in this course. So they're things you should always be looking out for, even if they're not recipes for always getting the job done. In this case, the correct approach is to think of a sum of squares. Sometimes sums of squares have clever disguises. Note that e to the 2x in this case can be thought of as e to the x all squared, as I've shown here, and in doing that, we can more clearly see the structure of a sum of squares. This one takes the form 1 plus u squared, but that requires us to think of e to the x as u. And if we're going to do that, we need to perform a substitution. So calculate du by taking the derivative of e to the x. And since e to the x is its own derivative, we get e to the x dx as the formula for du. Notice e to the x dx appears here in our numerator, so that entire chunk can be declared as du, which means completing the substitution leaves us with this easy integral of 1 over 1 plus u squared du. Notice this exactly matches one of the formulas given earlier, so we know now that this evaluates to arctan of u plus c. And don't forget to put u back in terms of x, and with that, you're finished this problem. That's all for the calculus of arctan, so I'll see you in the next video where we'll look at arcsecant.